Hello and thanks for watching my video. This video will be an explanation and analysis of my medium Fiffer trebuchet. If you haven't seen a Fiffer trebuchet before, check out First in Fright. They've got the big one that throws the farthest. Also, I have some videos explaining them on my channel. If you haven't seen it move before, here's a little bit of motion. Projectile comes down, this scissors moves forward. I've got a chain going over a cam, and that pulls the arm around and launches the projectile. Also note my full counterweight stall. As it comes down here, we get a full stall before releasing the projectile, which is pretty good. Now I'm using software here called Tracker. It's open source, free. If you would like to download it, just Google Physics Tracker and you'll find it, and it works pretty well. Now, to give you a little scale on this machine, it's this blue line from my throwing arm axle to the bottom of the machine, 1.37 meters. I got about 2 meters of counterweight fall. The machine's about, I'm going to switch units here, 8 feet tall. This is a 16-foot trailer. My counterweight is 355 kilograms, or about 800 pounds. And my projectile is 3.6 kilograms, or a little over 8 pounds. It's a milk jug filled with 1 gallon milk jug filled with water. Whenever you're analyzing a real-world object, you should check to make sure that your video matches the real-world results in some way. I've done that 3 ways. First, we look at the velocity here of when we're releasing the projectile, and it says 23 meters per second. If we assume no wind resistance at a 45-degree launch angle, that'll get you about 50 meters. And I stepped it off at 50 steps. I've got about a 1-yard step, so that's pretty close there. The second thing I noted on the graph showing the counterweight acceleration, you can see that while it's free falling, it's right around 10 meters per second squared, and the acceleration due to gravity is 9.8, so we're pretty close there. I also, in this frame, the projectile is 90 degrees to the arm, and I know the acceleration there, and the mass of the projectile, and the length of the arm, the length of the cam. I can figure out the tension in the chain. I got about 13.3 kilonewtons, or 3,000 pounds. It also tells me the acceleration of my counterweight here, and through the geometry of the linkage, I got a number within 1%. So we could assume that the video analysis is going to be accurate to our real-world scenario. The main item I want to talk about in this video is the advantage that the Fiffer design gives you, and it's all from this linkage here. When the projectile is or the counterweight is all the way up, you have a lot of leverage. The counterweight has a lot of leverage, meaning it can start falling, and it falls a long way before the pull bar really starts moving. Which allows it to free fall and gain the most velocity. Now, as it comes down, the leverage starts swinging the other direction, and if we were straight down, we'd have infinite leverage pulling backwards on this linkage. So you can see that our counterweight's fallen over 3/4 of the way. The pull bar has only moved half the way, and our arm has only moved, a little ways here. So as we keep coming down, the leverage gets so great that um, we actually end up stalling the counterweight. Now, so a stalled counterweight means we've taken all the energy out of the counterweight. So we could see in this graph, you know, we're released here, we're falling, and we've got negative velocity, we're moving downward. Our velocity is still negative, and then in between these two um, data points here, we switch from negative to positive. So in between 0.7 seconds and 0.73 seconds, we have stalled out our counterweight. Now, the counterweight does gain a slight upward velocity, which means we're lifting it, which we don't want. That's stealing energy from our projectile. But that can be fixed with tuning. A lot of people talk about wanting a counterweight stall, but it's not many machine designs allow you to receive that. Along with the counterweight stall, you can see the accelerations of our counterweight. So here, here's free fall. Here it starts picking up, pulling on the pull bars, pulling on the chain, and in here, this is where our projectile starts whipping around, and we get to peak here. 38 meters per second is our upward acceleration. So that's 4 G's pulling up on the counterweight. Now this is happening at the same time as the projectile is accelerating, and you can see here that from the start to half a second, not much has happened with our projectile, but in this last 0.2 seconds our acceleration goes way up. Now this is happening right in here. We've started with the projectile right in close to the arm, and so it's not accelerating much, but when it starts coming out away from the arm, it's accelerating the most, pulling the hardest. You can see here where it's 90 degrees from the arm, where it's got the most leverage against the arm. That's also where we're getting the most upward acceleration on our counterweight, and then we swing the rest of the way around and release it. And that's something that's not necessarily specific to the Fiffer. A lot of machines these days will store their projectile real close to the throwing arm axle, and then allow it to swing around. And I think that really helps take energy. It's pulling harder. It's really taking energy back away from the counterweight and putting it into your projectile. So LD Vance would want us to talk about where's the energy in our machine and how much are we getting into the projectile. So if I count from where the counterweight, if I raise it from here, the lowest point to the top, I'm only getting about 25% of my energy into my counterweight. Now, I've got my counterweight stall at this height. This here's rubber bumper with wood underneath. If I move that up 4 inches, then that would probably make me 10% more efficient, simply because this is where my stall is happening and my projectile is releasing, and I wouldn't count this here. If I look at the peak velocity of my counterweight, so the peak velocity is right here. We're at 3.8 meters per second. If I view that as kinetic energy, I'm getting about 40% of the kinetic energy from my projectile from my counterweight into my projectile. Now I did say that my counterweight starts moving up. We could see the velocity of the counterweight right here, somewhere between the 0.7 second mark is when our counterweight starts going up. Now on our video, that's between these two frames, and in the very next frame we've released the projectile. Now some of this is from the trailer bouncing up. When we look at the graphs of the projectile, we can see that the projectile has positive acceleration the entire time, and the velocity is going up the entire time. So that lets us know that we actually haven't taken any energy away from the projectile. It's all in there. The bouncing up is, I think, coming from the trailer. So that's a little misleading on our data here. I don't think we would get this positive velocity if the machine was mounted on the ground instead of on a trailer. So if I got 40% of my energy into my projectile, where did the remaining 60% end up? Well, I think the biggest hog of my energy is my trailer. I'm not really sure what the capacity of my trailer is, but it takes a fair amount to squat the shocks down, and you can see here that I squished the trailer down 3 inches maybe. So that has taken a lot of energy out. Plus, the video started, these were in the same location, so my whole machine has jumped backwards, about 4 inches or so. How would I fix these problems? Well, first, the competition, I normally block my trailer so it doesn't squish. I didn't do that here because I was just hurriedly testing my machine. So either block my trailer or set the machine on the ground. Plus, I could stake it or strap it so that the machine didn't move backwards. And I think I would gain a fair amount of efficiency just by doing those two little things. Energy loss due to friction is also a big factor. All of my axles are just steel axles going through wood, so I don't have any bushings or bearings in those. Plus, some of my axles aren't very well aligned. I had some drilling inaccuracies or measuring inaccuracies when I made a couple of my axle holes, so I'm losing some there. The traditional Fiffer would have a pin in the back and an arm coming out that would guide the counterweight path. Instead, I've chosen to use a vertical guide similar to an F2K or a fat trebuchet. And at the bottom here, it's really pulling pretty hard. And like I said, about 13 kilonewtons, 3,000 pounds pulling back. Now I get to divide that. Half of it's going up here, half of it's going down here. I looked up the coefficient of friction. Steel on wood is about 0.2. And now I've waxed the wood. I couldn't find a coefficient for that. I think that's helping me quite a bit compared to the 0.2. So if it was 0.2, that would be about 5% of my energy would be lost just right there rubbing. So I figured probably 2%. I think the wax is making it twice as slippery. Finally, what would I improve on this machine? Well, the first thing, as I mentioned before, is that either block my trailer or put the machine on the ground so I don't lose the energy there. I also was thinking, when I first ran this machine, I was actually I had the chain and cam set up so that my arm, instead of being straight down here, my arm was horizontal with the projectile sitting on top of it. The problem with that was when my arm was here is where I was getting my counterweight stall. My counterweight had fallen down a little farther, the arm was straight back, and I could only get it to throw up or backwards. So when I realized the stall was happening in the wrong spot, I shortened this chain and put the arm straight down, and then I set the projectile as a temporary measure on this log here. Now I've realized that maybe what I should have done instead of shortening the chain would have been to shorten the arm so that it would have less leverage and let my counterweight fall just a little farther. Every couple inches down I gain is more energy. So I'm not sure where the diminishing returns would be. My arm's already pretty short, but that's something I'd like to test as well. Well, I think that's about it for this video. If you have any questions or comments, please leave them below. And good luck chucking.